Okay, so my talk is Fantastic Voyage 3, Destination Beam. If you are not like me and have watched a lot of schlocky 1960s sci-fi movies, there's a really wonderful movie I would suggest called Fantastic Voyage, where people take a tiny submarine into a dying scientist and clear a brain clot out. My goal for this talk was to take you as deep into a very simple program as possible in 20 minutes. And studiously avoid the parts of this program that are way too complicated to talk about in 20 minutes, such as hype or locking or things like that. And we'll call them out. So what is the subject of this talk? What is the program that we're going to explore? Well, it's a program that I've called Simple. And it's called Simple because there's not much to it. There is a Simple Supervisor because it is a proper OTP application. Simple Supervisor looks pretty much like you would expect. It has two processes that it is supervising. One called Simple Send, the other called Simple Receive. So that's sort of their theoretical layout. Simple Supervisor has a monitor. If you've never looked inside of Gen Supervisor, it maintains a monitor on the process. Simple Send is a Gen server that sends itself a message every so often. Here's the setup for that. The initial trigger is the sort of common Erlang send after trick that people do into a Gen server, and then the messaging. So sends itself trigger. When it receives the trigger message, it then sends simple message to simple receive. And then the subsequent trigger, which incidentally, if you do this, your timers will eventually drift. Try it out. It's pretty fun. So Gen server call. We're using call to send a message to simple send. How does call actually function? So we are now inside of Gen server. This is the implementation of call. And it turns out Gen server call is implemented in terms of a thing called Gen call, which Gen is not a thing that is exposed in documentation. So now we've sort of peeled back the layers behind the private implementation of things. So let's look at Gen call, and it's worth noting, keep in mind that atom there called Gen call, or $ Gen call. That'll be important later. So now we're inside of Gen's call, and it's not very interesting, and in fact, it's mostly just done in terms of a thing called do call. So let's look at do call. So do call is a really big function, and the important thing to note at the start of do call is that it takes out a monitor on the process that is going to be sent a message. So the receiver, sometimes the code base will call it to, so you'll see that back and forth. So whenever a call happens, implicitly a monitor is being taken out. So the message send is actually in terms of just Erlang send. We see the process, which is the to or the receiver. We see an interesting little tag structure here. So the label, which we know from sort of introspection and memory, is the gen call. We see an inner structure in the tuple, a self and an mref. So that'll be important later, but it's a way for this process to smuggle enough information about itself to the receiving process to get a message back. Because if you recall, Gen server call allows the sent process or the receiving process to send you a response back. And then no connect is something we'll just totally ignore. So here is the same diagram. Simple send is sending, simple receive, but we left a part out because there's actually an implicit monitor here that we don't control. So now we're back in Gen server. So this is where the receiver is handling the sent message. Oh, the lights came on. Here's where Gen call is important again. That label is what Gen called it, because once we are back in the handle message, if you look in the Gen server code base, there are actually several different clauses that can match. Gen call is the one that happens to match, and there go the lights. Gen call is the one that happens to match for the call from Gen server to another thing. So this is a Gen server to Gen server communication. So try handle call is the thing that invokes the user-defined callback. So let's pop to that. So in simple receive, when you get simple message, you send back the total number of messages that you've received, updating your state to 1. So now we've sort of seen the machinery of how a Gen server calls a Gen server. So we pop back into the Gen server implementation, and we see the reply. So here's where the smuggled information gets important. Reply is actually brutally simple. To tag, which is the self and the mref. The mref is then used as a tag so that the Gen server that initiates the message knows that the Gen server that sends the message back is actually the one that got the message or a proxy. So we're able to track that the correct message has streamed through the system because you don't want miscommunication between like multiple processes that are coordinating to answer your message. And so we get the message back. and it's upside down. All right, so back in Gen, we have already sent the message. We've called Erlang send, and now we do the receive. So here's the point where it comes back to the sender. You'll see that the mref is used to detect that the correct message has returned back, because any arbitrary process in the system can just send a message. So now we've validated that the correct message has come back from the correct thing using a selective receive. And we also get a down message. So if we try to send something, the process crashes, we'll know without having to wait for a timeout. Okay, so now the message is done, the monitor's gone. So, where do we go from here? Let's actually dig in further. So let's back up to Gen, and let's look at the Erlang send that's embedded in send. And this really encapsulates the rest of all we care about in this talk, is this one line. So the first thing we'll investigate is Erlang send itself. How does send actually work? And sort of on the flip side, because we're already digging around in the C code, how does receive work? And the second thing that we'll concern ourselves with, how does name resolution work? So let's get in our tiny little shrinky-dink submarine. Tristan, I told you there would be a submarine. So most of Erlang is actually written in Erlang, and that's great. If you didn't catch the Erlang kernel talk that happened not 5 minutes ago, you should go catch it, because it's all about the Erlang kernel. It's mostly all in Erlang. But if you want to get into these BIFs, you start getting into the implementation of the beam, which is sort of C itself. And if you don't know C, this is a great project to sort of learn it, because it's a wonderful example of sort of historical C and new C and a lot of macros, and it's a really great project to cut your teeth on. Okay, so let's talk about Erlang send. So simple is too big for us to sort of understand at the micro level that we're looking to get into it. So I've made another tinier program called trimmed. And trimmed spawns a child process. The child process is responsible for sending information back to the parent, et cetera, et cetera. Pretty straightforward. There are 2 points. There's a bang and there's a send. So is there actually a difference between bang and send? So we'll explore that. But first, we need to generate core, because we need to know what Erlang actually understands about this program at a deeper level. So here's part of the core of trimmed. The implementation of trimmed in core is pretty long and pretty gnarly. But if we sort of dig around in there, we'll find at one point a thing called Erlang : bang is being called. And then at another point, we'll find a thing called Erlang : send is being called. So these are BIFs, right? So let's go look up BIFs. And if you sort of muck around in the Erlang code base for a while, you'll find a thing called Erlang.erl. And then you will find that the implementation of send is done in terms of this NIF error. So if you've ever written a NIF, you know that you have sort of the Erlang shell over the top of it, and then a thing gets linked into the VM, and then there's a resolution that occurs. So this is just found by searching in the code base. So we need to find out where the BIF is actually implemented. So where is the BIF table in Beam? So if you ever implement your own NIF, you know there's sort of like a situation that you have to do to set up the table. There are so many of these in Erlang that there's not actually one place where they're all listed out. It's actually generated. So it turns out there's a script called Ertz emulator utils make tables, which I found by just noticing that there was a BIF export and a thing called BIF or beam BIF load.c, which I guessed was related to loading BIFs. This was like an hour of me mucking around. And if you sort of explore these large code bases, you'll end up spending a long time just sort of mucking around and drinking coffee. So I then sort of grepped my way through, and I found extern export BIF export on line 234 of make tables. But basically, it's all in one of these .tab files. So the .tab files, BIF.tab, which is the one that we happen to care about, has a very helpful header that explains how the BIF tab file is laid out. And if we sort of muck around even further, we'll eventually find that Erlang bang, Erlang send all map to this thing called ebif bang2. Ebif bang2 is defined in a file called bif.c, which happens to be defined in terms of a thing called Erl send. As an aside, the bif underscore things are actually macros. And my favorite macro is bif_p, which is defined as a underscore underscore lowercase p. So let's talk about Erl send. Oh, incidentally, bif_p is a macro that says the process bif_arg a is the first argument of the et cetera, et cetera, et cetera. They are actually named pretty well. I have no idea what a underscore underscore p is. So bif.c, if we look for Erl send, send is a short prelude for manipulating process context and a big old switch table for deciding what to do with the results of a thing called do send. Now, you're not really meant to be able to read this. What we care about, come on, is a function in here called do send. So there's a lot to do with sort of locking and things like that. And unfortunately, because I only have 10 minutes left, we won't really go into locking, but locking in the beam is fascinating. So do send is even longer, in fact, longer than that. But the important part is this this label message called send message. So in some cases, a process will send itself a message. The scheduler thread holds locks about that message, or excuse me, about that process. So you would deadlock the system or do otherwise goofy things by having a process try and take out its own lock that it already holds because the schedule holds it. So there's a lot of special casing around these sorts of situations in the beam. What we actually care about here, because we can't go into locking, is a thing called Ertz send message, which is in a module called Erlang message. Now, what I've done is I've cut out a lot of if-def code here because it was much, much longer than the implementation of do send. As you might expect in a language where passing messages and sending messages and whatnot is a very important thing, there's a lot of optimization that goes into sending, and there are a lot of optimizations that are only flagged on if you give it the right flag at compile time. But the important part for our use case is this part in Erlang send. So it's possible for a message to, or a process to send itself a message, in which case that message is already allocated in the process's heap, so there's no reason to do extra allocations. It just sort of says, great, I have this message, here we go. If you are sending a message to another process, it's kind of a two-phase step. First, you have to allocate the message in the receiver process's heap, which is what Ertz allocate message heap stats does. And then you have to signal to the process that there is, in fact, a message available for it on its queue. So what is queue message? And queue message is actually a function that is delightfully commented, which is not at all typical in the beam in some places. What is queue message? The important part here is it's implemented in terms of a thing called queue message, so we'll dig into queue message. There's a whole bunch of debugging set up at the top. There's locking manipulation. So what's actually important here is this part. First, we immediately place the message on the queue if certain messages apply, or certain conditions apply, I should say, in terms of a macro called link message, which should suggest that a message is being linked into some type of queue. And link message is, in fact, a macro that does an operation on a linked list. So it turns out that Erlang process queues are linked lists in the standard sort of like pointer chasing method that if you did any sort of computer science work at university, you are deeply, brutally familiar with. If those conditions are not held, then there is a delayed placement in terms of a thing called Ertz and queue signals. So we've already done all the work to allocate the message in the receiver, but there are some conditions where we can't link the message directly into the process's message queue. So we sort of, pop into Ertz and queue signal, and we get a thing called Ertz in queue signal. It actually turns out if you pop into the definition of the process, and by definition of the process, I mean the struct that is the process, there will be a helpful comment in there that will explain, if you chase a couple more comments in through other files, that there is a thing called an inner and a middle queue. So the middle queue is for queued messages that are in transit, meaning that the sender isn't able to sort of place them on the queue directly, but you can signal to the process that there is a message there for it when it gets around to it. So that allows the sender to not block. Inner messages are basically the opposite of that. They immediately go into the queue. In-queue signals is a long function, and we'll skip it. So now what about receive? So we've sort of dug down as far as we can go into Erlang send. We've chased through many, many different types of C files and headers. Is there, in fact, a BIF for receive? Well, it turns out that receive is such a special case thing that it's actually more of an a series of optimization passes than a single type of BIF, because there are actually lots of different types of receives, whether they match, whether there's timeout, things like that. So you want to generate different code for these types of things. So exactly what gets emitted is up to the optimizer, and we'll only examine a certain part of this because it happens to be sort of the reverse of the in-queuing that we've just looked at in Erlang send. So let's look at a thing called remove message, which is sort of in the middle of this potential diagram of what a receive turns into. There's a lot here, but if we zoom in, we'll find this friendly thing called Unlink Message, and if we sort of jump into Unlink Message, we'll see that it's basically the opposite of the linked list work that we saw earlier in Link Messages. So sending a message from one process to another, if both processes are the same, you don't do reallocation, you just sort of fiddle with a queue. If you are sending from one message to another and both processes are distinct, there's a condition whether or not you can get the appropriate locks to allocate and in place directly or not. So what about PID.name? So now that we have send receive, now we need to go back and understand sort of how process messages are resolved. So if we pop all the way back out to do send, which was in biff.c, which if you will remember 10 minutes ago, I guess, was where we started all of this. This was a big switch table. That big switch table, which we didn't really go into at the time, was to do with the nature of the process that was being examined. So if we are sending to a port, we have to do different things. If we are sending directly to a PID, we don't have to do anything because we already know the nature of the process, or rather, I believe it's called an internal PID. If it's an external PID, it goes through a port, et cetera. But we're interested in the case where the to is an atom. That implies that this is a name that needs to be resolved into a PID or any of the related natures of a PID from the point of view of the beam. So this is our entry point, and in particular, we're interested in this function called erts, where is name to ID. So let's pop into that. It kind of fits on the screen, unlike some of the other things we've seen, but if we zoom in, we'll find this thing. So this little bucket here, if you've ever done any undergraduate computer science, you should be also brutally familiar with this structure, is what's called a bucketing hash map. So a bucketing hash map is an array of linked lists, and you take your entry point, you modulo it something, basically you compute the hash of it, you decide which bucket it goes in, and then you search for a spot. So what this implies is that the Erlang name hash map is a bucketing hash map. Protected by locks, which is not reflected here. That's actually up at the top of this function. So if you are reading a name, if you are looking one up, you only need to take a read lock. If you are writing a name or registering a name, you have to take a read-write lock. And unfortunately, we only have 3 minutes left, and we can't go into locking. But this is inlined. There's a comment. Actually, the comment preserved is that we have inlined code from hash.c for speed. I don't know if that is entirely true anymore because of the way C compilers work, but it was probably true in the early 90s. So the next bit of the code is the bucket seek. So we found which bucket the entry should be in, and now we have to just do this linear search through the linked list to find the name entry. And there are some conditions here for whether or not we found it. There are things called common IDs and whatnot, and I highly encourage you to go seek out the process struct and figure out what that is. So that's how looking up of a name is done. There's a read-write lock, or there's a read lock, I should say, on the global hash map. Exactly where the hash map is established and when, we won't go into. So if we pop back up to biff.c, and we already sort of know that register is going to be a biff, and we don't have to do all this searching through Erlang.Erl, but we can look in the biff tab and see that, in fact, there is this biff called register2. The important part in that is a thing called erts register name, which if we pop into that function is really big, just like the other one was, but the important, even bigger, but the important part is going to be this part. And if you sort of squint, you'll find this function called hash put. Before we get to this point, there's a lot of work to figure out the exact nature of the thing that's being put into the hash map, but at this point it's all resolved into a nice PID and atom name. And if we jump into a file called hash.c, we'll find this hash put, and it is the reverse of the lookup. It's a bucketing hash map of linked lists. So we sort of figure out which bucket it should go in, we find a spot for it, and we pop it in there. Okay, so now we've seen how send and receive work. We know how the lookup and registration of names work, and that is basically the end of this talk. So we've skipped a ton of stuff. Right, like we've skipped logging entirely, we've skipped garbage collection, we've skipped distribution. Like I said, most of Erlang is written in Erlang, so if you're very interested in the internal implementation details of Erlang, you really don't have to know C. But if you start getting interested in sort of these very particular fiddly details of Erlang, like if you're interested more in how all receives everywhere work, you kind of need to know C and the compiler infrastructure and things like that. And I highly recommend it. It makes for fun weekends to sort of dig through all of this. So hopefully you feel a little more comfortable doing that now. And, thank you, everyone who's ever worked on the Beam. It's an impressive piece of code. Thank you.
So apparently I'm not even qualified for QA because I started us a few minutes early. I read the paper wrong. So I think we have a few extra minutes for questions that we otherwise would have had. So
Explain the lots. It is actually a really neat hierarchical system. But a few minutes will not do it. Another talk would be great, though.
Is there a piece of code in the Beam that you tried to understand but could not?
Is there many? Actually, I don't know if anyone can hear me. So So I am a low-level systems engineer. I have a pretty work-a-day understanding of how the locking should work, but to truly understand it, I would need to step through the Beam with GDB and sort of poke at it. So theoretically, I understand how it functions. Practically, could I make changes to it? Absolutely not. Especially because the C implementation of Beam doesn't use atomics that I understand, like the C standard atomics. So I need to explore sort of how those have been implemented and how they are reflected on the CPU architectures that are supported.
How many weekends did it take you to get this deep into the Beam for the first time?
is that mic on? Okay. Right now.
How's this? Okay, cool. So how many weekends did it take? So I actually posted on Twitter my research notes for this talk, which I normally don't do. I think most talks that I do take around 200 hours to put together, and I guess this one probably would take about that same amount of time. Some of that is practice, like trying to make sure that I got this thing in under 20 minutes was a fun time. In terms of just sitting down and reading, probably 4 or 5 Saturdays, I would say, and a couple of weekend nights, things like that. So the question was, how much is this going to change in more modern versions of Erlang? So the fun thing is, when I worked for a company called AdRoll, I did kind of a deep dive on certain parts of the Beam, ETS in particular, and all of that had radically changed in the few years that So to answer your question, I would assume that it's all going to change very rapidly. And the person to actually ask is Lucas, who's sitting directly between us. He should have a much better understanding of that. But there are parts of it that are clearly venerable, and then there are parts of it that are changing pretty rapidly. The optimization passes were all new to me, for instance. Any more questions? There's a door behind me.
All right. Thank you, Brian.
Thank you all.